Hi everyone, I'm Ting-Chao Chou, a theoretical biologist and pharmacologist, retired 10 years ago. Today I would like to share with you the highlights of my lifetime theoretical work on mass action law dynamics and applications, from in vitro to in vivo studies, including cancer research and infectious diseases. This is the abstract for those who might find it interesting. Over 50 years ago, I asked a seemingly simple question. I1 and I2 each inhibit 30%. If additive effect would inhibit how many percent? But it was difficult to deal with. So I spent my lifetime to explore it. Now I would like to quickly tell my story and my major conclusions. The mathematical approach that I use for the mass action law has been a new concept, which allows derivation of the median effect equation as the unified general dynamic theory, and then develop further into pharmacodynamics, biodynamics, and bioinformatics. The median effect equation of mass action law is the unified theory that determines potency and shape of those effect curves and dynamic parameters. The combination index equation quantitatively determines synergism as a Ci smaller than 1, additive effect as Ci equal 1, and antagonism of Ci greater than 1. The dose reduction index equation determines how many fold dose reduction for each drug during synergism. It took me 16 years to derive them and to develop computer software to simulate them. The most important feature is that all terms of these three general equations are dimensionless relativity ratio, thus independent of unit, physical state, size, and the complexity of mechanism. Therefore, the MAL theory has unlimited applications. The MAL theory turned out to be very important in overall scientific R&D. A symposium article in 1984, published in a small journal, now received 8,200 citations, including a record number of 1,520 journals. Based on the Google Scholar citation, the top 3 major articles of MAL theory application have received a total of 19,000 citations internationally. Based on the Web of Science, among the 29,000 citations and 1,350 citing patents internationally, including indicating that it has contribute significantly in scientific R&D. These are examples of pattern listing use the MAL theory method during the past 3.5 years. My 11-chapter book entitled Mass Action Law and Algorithm for Translational and Precision Medicine Informatics will be published next month by Academic Press and elsewhere. It opens up a new avenue for the MAL theory-based R&D that is cost-effective, efficient, and is complementary alternative to the traditional statistics-based R&D. Now let's go through the theoretical part quickly. The median equation is the unified general equation for Minkes-Menten equation for enzyme kinetics, Henderson-Hasselbalch equation for pH ionization, Hill equation for higher order ligands, and the structural equation for receptor binding. In short, the median effect equation, also called doctrine of the median, is defined by FA over FU equal D over Dm to the mth power. In other words, the ratio of fraction affected versus the ratio versus the fraction unaffected is equal to the ratio of dose versus median effect dose to the mth power. Dm value signify potency, and the m value signify dynamic order and the shape of dose curve. This slide shows that median dose is the universal reference point, and dynamic order common link. Most significantly, the computer simulation of median effect equation with the median effect plot linearize all those effect curves with different shapes and different potencies. This linearization approach leads to the minimum two-dose data point theory that adds two doses by default. These two doses are dose 0 and the median effect dose. Thus, ML theory leads to efficient, cost-effective, econo-green scientific R&D. It is especially beneficial in animal studies and clinical trial protocol design, digital data analysis, and quantitative conclusions. The drug combination synergy determination has been a controversy over 100 years. My argument is, if no clear definition for synergy, then NIH, FDA, US Patent Office, and editors, reviewers have no basis to argue or to regulate the synergy claims. Now, the CI method provides a clear-cut digital definition for synergies. Here is the ML dynamic-based algorithm for computer simulation of synergies. The ME interface with the CIE that lead to simulation of CI value at different effect levels, thus determine synergism, additive effect, and antagonism. After multiple dose data point entry to computer for single drugs and drug combinations, it takes only 1 second to simulate for 2 drug combination studies. The computing is the third generation software derived in 2004. It is offered for free download by PD Science LLC since 2012 at the website www.composing.com. During the past 12 years, it has over 50,000 downloads from scientists of over 137 countries. The earlier edition of software in 1980s and 90s, including Calculus, all based on Massagendo PD, BD, CI, and DI theory, and all published by the Biosoft in Cambridge, United Kingdom. The computing software generates 4 diagnostic plots. The FACI plot simulates CI value at all effect levels. CI equal 1 is additive effect, smaller than 1 is synergism, greater than 1 is antagonism. Isobologram shows when combination dose data point fall on the diagonal or hypotenuse, it's additive effect. If fall on lower left, it's synergism. Fall on upper right is antagonism. It can also generate those normalized isobologram. In the dose reduction index here, DRI equal 1 indicate no dose reduction. When DRI greater than 1 indicate favorable, smaller than 1 indicate unfavorable dose reduction. The trend over the past 5 years show that the CI method is by far more widely used than any other method for synergy determination. This slide illustrates that MAL dynamic theory-based top-down R&D approach is opposite yet complementary alternative to the traditional observatory statistic-based bottom-up R&D approach. The traditional approach usually has specific aims to propose method statistical analysis, but their conclusions are frequently statistics with p-values. This diagram shows how the Mikate-Menten equation, combination in the equation, and dose reduction in the equation have unlimited applications. And all 3 unified equations use 1 as universal standard. This leads to the unity of 1 theory for the mathematical and the philosophical concepts. Now let's move on to virology. Using Massagendo theory and anti-HIV agent as examples. The Massagendo PD focus on synergy determination, cost effectiveness, cocktail design, and attacking different stages of life cycle of virus. This is a typical two-drug combination design in vitro. Drug 1, drug 2, and combinations. Each has only 5 drug data points in duplicate or triplicate assays. For MLPD guided best design and best efficiency, I recommend using the constant ratio combinations as shown in diagonal scheme. This is a real data anti-HIV example for AZT and interferon in vitro, single drug and their combination. It used only 15 dose data points. The experiment usually took only 2 to 3 weeks to complete. The computer simulator took about 1 second, which generated computer report printout for about 10 pages, including dynamic parameters, tables, diagnostic plots for quantitative conclusions. The computer report printout has about 10 pages. These are abbreviated examples for experimental description and automatically determined dynamic parameters. This is the combination index table and FACI plot. This is dose reduction index table and FADRI plot. Here shows an example of summary table for 2 to 5 drug anti-HIV drug combinations. It shows the DRI and the CI values at IC50, IC70, IC90, and IC95. These are the example of FACI plot of anti-HIV 2 and 3 drug combination, showing synergism or antagonism. Most of these results came from my collaboration with Professor Martin Hirsch of Infectious Disease Unit, Mass General Hospital at the Harvard Medical School. This is the polygonogram that I introduced in 1988. It is very useful for cocktail design and useful for semi-quantitative projections and predictions. This slide summarizes early anti-HIV history. Most of them use drug combinations. This general approach can also be used for other viruses, such as herpes, COVID, in addition to vaccination therapy. This slide shows some example of anti-HIV agents, which we will skip. This slide now shows a comparison of 2 anti-HIV clinical trials. One trial is for AZT plus VTC using traditional statistical method, which used 366 patients. However, AZT used only 1 dose and used a statistical p-value for conclusions. In another trial for AGT and interferon alpha, use the machine dynamic design and computer analysis using only 36 patients. Both AGT and interferon use 3 doses and use the constant ratio combination design, which quantitatively determines synergism, as indicated by CI smaller than 1. Show efficiency, cost effectiveness, quantitative, and using 10 times fewer number of patients. This is the actual example of MALPD-based clinical trial protocol design and layout. Here with a constant combination ratio of 25:1. This slide shows original references of AGT and interferon clinical trial. More recent development of reference in this area are shown here for broader multidisciplinary applications in scientific R&D. The computing software can solve many practical dynamic questions. It can simulate CI value at different effect levels and different dose levels. The contraction isobologram help finding the best combination ratio and the best sequence of drug combination regimens. Theoretically, the CI value for n-drug combination has been developed, but practically hard to do such a big experiment. This is the geographic map of my article citations generated by Web of Science. It had very detailed information. Here is the summary or conclusion for the MALPD theory and applications in 5 major points. There have many favorable features for scientific R&D, such as efficient complementary alternatives, digital automation, cost-effectiveness with unlimited applicability, cross-disciplinary application, and informatic guidance. Thank you very much for listening.